Hey everyone, welcome to today's class, where we're diving into the world of logic with the classical square of opposition and immediate inference. These concepts might sound a bit fancy, but don't worry, we're going to break them down and make them super easy to understand. Plus, we'll be solving some UGC NET previous year questions to see how these theories play out in real exam scenarios. By the end of this class, you'll be a pro at handling these logical propositions. And if you're craving even more practice, there's a link in the description below that you can click on to find additional resources. Let's get started and have some fun with logic. Classical square of opposition. The square of opposition is a tool used in traditional logic to show how four types of statements about the same subject and predicate are related. These four types of statements are A. Every S is P, e.g. every swan is white. E. No S is P, e.g. no swan is white. I. Some S is P, e.g. some swans are white. O. Some S is not P, e.g. some swans are not white. On the square, these statements have specific relationships. Contrary, every S is P, A versus no S is P, E, both can't be true at the same time, but both can be false. Contradictory, every S is P, A versus some S is not P, O. One must be true and the other must be false. Subcontrary, some S is P, I versus some S is not P, O. Both can't be false, but both can be true. Subaltern, every S is P, A implies some S is P, I, and no S is P, E implies some S is not P. The truth of the universal statement implies the truth of the particular statement. These relationships help us understand how the truth or falsity of one statement affects the others. Imagine you have a group of four friends: Alice, Bob, Carol, and Dave. They each have different opinions about whether all birds can fly. Here's how their opinions are organized. Alice says, all birds can fly. This is called a universal affirmative statement, written as A. Bob says, no birds can fly. This is a universal negative statement, written as E. Carol says, some birds can fly. This is a particular affirmative statement, written as I. Dave says, some birds cannot fly. This is a particular negative statement, written as O. Now let's imagine a square where each corner has one of these friends statements. The classical square of opposition shows how these statements are related to each other. Contrary, A and E, Alice and Bob are directly opposite each other. If Alice says all birds can fly and Bob says no birds can fly, they cannot both be right. One of them must be wrong, but they can both be wrong. Subcontrary, I and O, Carol and Dave are directly opposite each other at the bottom. If Carol says some birds can fly and Dave says some birds cannot fly, they cannot both be wrong, but they can both be right. Contradictory, A and O, E and I. Alice and Dave, and Bob and Carol are diagonal from each other. If Alice says all birds can fly and Dave says some birds cannot fly, one of them must be right and the other must be wrong. The same goes for Bob and Carol. Subaltern, A to I, E to O. Alice's statement, all birds can fly, implies Carol's statement, some birds can fly. Similarly, Bob's statement, no birds can fly, implies Dave's statement, some birds cannot fly. If Alice or Bob are right, then Carol or Dave must be right too. But if Carol or Dave are wrong, it doesn't necessarily mean Alice or Bob are wrong. Understanding questions from the classical square of opposition. The classical square of opposition is a fundamental concept in traditional logic, illustrating how different types of categorical propositions relate to each other. If you're studying this topic, here are the three main types of questions you might encounter, explained in an informal and easy-to-understand way. 1. The first type of question might simply ask you to identify or define the different relationships within the classical square of opposition. Here's a quick overview. Contradictory. This relationship occurs between pairs where if one statement is true, the other must be false, and vice versa. For example, all swans are white, A, and some swans are not white, O. Contrary. In this relationship, both statements cannot be true at the same time, but they can both be false. For example, all swans are white, A, and no swans are white, E. Subcontrary. Here, both statements cannot be false at the same time, but they can both be true. For example, some swans are white, I, and some swans are not white, O. Subaltern. This relationship means that if the universal statement is true, the particular statement must be true as well. For example, if all swans are white, A is true, then some swans are white, I, must also be true. Similarly, if no swans are white, E is true, then some swans are not white, O, must also be true. 2. Combination questions. The second type of question might ask you to match each relationship with the correct pairs of statements. Here's how you can remember these combinations. Contradictory, AO and IE. A, all swans are white, and O, some swans are not white. I, some swans are white, and E, no swans are white. Contrary, AE. A, all swans are white, and E, no swans are white. Subcontrary, IO. I, some swans are white, and O, some swans are not white. Subaltern. A, all swans are white, and I, some swans are white. E, no swans are white, and O, some swans are not white. 3. Truth and falsehood questions. The third type of question involves understanding how the truth or falsehood of one proposition affects the others. Here's a breakdown of how this works. If a contradictory statement, AO or IE, is true, the other must be false. For example, if all swans are white, A is true, then some swans are not white, O, must be false. If a contrary statement, AE, is true, the other must be false, but they can both be false. For example, if all swans are white, A is true, then no swans are white, E, must be false. However, it's possible that neither all swans are white nor no swans are white is true. If a subcontrary statement, IO, is false, the other must be true, but they can both be true. For example, if some swans are white is false, then some swans are not white, O, must be true. If a subaltern statement, AI or EO, is true, the particular statement must be true as well. For example, if all swans are white, A is true, then some swans are Y must also be true. If no swans are white, E is true, then some swans are not white, O, must also be true. Question 1. Which of the following statements are so related that if one of them is true, the other must be false, even though both of them can be false? A. Some adults are farsighted. B. No adults are farsighted. C. All adults are farsighted. D. Some adults are not farsighted. Explanations. To determine which statements are so related that if one of them is true, the other must be false, even though both of them can be false, we need to identify the contrary relationship. Given statements. A. Some adults are farsighted. Particular affirmative. I. No adults are farsighted. Universal negative. E. C. All adults are farsighted. Universal affirmative. A. D. Some adults are not farsighted. Particular negative. O. Analysis of the statements. A and DA. Some adults are farsighted, and D. Some adults are not farsighted, are subcontraries. They cannot both be false, but they can both be true. This does not fit the requirement. C and D. C. All adults are farsighted, and D. Some adults are not farsighted, are contradictories. If one is true, the other must be false. This does not fit the requirement of both being able to be false. A and B. A. Some adults are farsighted, and B. No adults are farsighted, are contradictories. If one is true, the other must be false. This does not fit the requirement of both being able to be false. B and C. B. No adults are farsighted, and C. All adults are farsighted, are contraries. Both cannot be true at the same time, but they can both be false. This fits the requirement. Correct answer. The correct answer is B and C only. This option correctly identifies the statements that are so related that if one of them is true, the other must be false, even though both of them can be false. Question 2. Which of the following statements are contrary to each other? A. All movies are thrillers. B. Some movies are not thrillers. C. No movies are thrillers. D. Some movies are thrillers. Explanations. Understanding contrary. Contrary. Two statements are contrary if they cannot both be true at the same time, but they can both be false. Given statements. All movies are thrillers. This is a universal affirmative statement, or A statement. All S are P. B. Some movies are not thrillers. This is a particular negative statement, or O statement. Some S are not P. C. No movies are thrillers. This is a universal negative statement, or E statement. No S are P. D. Some movies are thrillers. This is a particular affirmative statement, or I statement. Some S are P. Applying the contrary relationship. Contrary statements are A and E. A. All movies are thrillers. E. No movies are thrillers. These two statements are contrary because they cannot both be true at the same time. It's impossible for all movies are thrillers and no movies are thrillers to both be true. they can both be false. For instance, it is possible that some movies are thrillers and some are not. Evaluating the options. A and C only. A, all movies are thrillers, and C, no movies are thrillers, are contrary statements. This matches our understanding of contrary relationships. B and C only. B, some movies are not thrillers, and C, no movies are thrillers, are not contraries. They are in a subcontrary relationship where both can't be false, but both can be true. A and D only. A, all movies are thrillers, and D, some movies are thrillers, are not contraries. All movies are thrillers implies some movies are thrillers, meaning A is true and so is D, but it doesn't fit the definition of contrary. C and D only. C, no movies are thrillers, and D, some movies are thrillers, are not contraries. They are contradictory statements, meaning if one is true, the other must be false. Correct answer. The correct answer is 1. A and C only. This option correctly identifies the statements that are contrary to each other. Question 3. Which of the following statements are so related that they cannot both be false, although they can both be true? A. Some professors are spiritualists. B. All professors are spiritualists. C. No professors are spiritualists. D. Some professors are not spiritualists. Explanations. Subcontrary. Two statements are subcontrary if they cannot both be false at the same time, but they can both be true. A. Some professors are spiritualists. I statement, some S are P. B. All professors are spiritualists. Statement, all S are P. C. No professors are spiritualists. E statement, no S are P. D. Some professors are not spiritualists. O statement, some S are not P. Applying the subcontrary relationship, subcontrary pairs are, and O, some S are P and some S are not P. Now let's examine the given options, B and C only. B, all professors are spiritualists, and C, no professors are spiritualists, are contrary. They cannot both be true, but they can both be false. B and D only. B, all professors are spiritualists, and D, some professors are not spiritualists, are not subcontraries or contraries. All SRP implies some SRP, which means B and D cannot be evaluated as subcontraries. A and D only. A, some professors are spiritualists, and D, some professors are not spiritualists, are subcontraries. They cannot both be false at the same time, but they can both be true. If one is true, it does not force the other to be false. A and C only. A, some professors are spiritualists, and C, no professors are spiritualists, are not related in a subcontrary relationship. Correct answer. The correct answer is A and D only. This option correctly identifies the statements that cannot both be false, although they can both be true, adhering to the subcontrary relationship in the classical square of opposition. Question 4. Which of the following statements are correct? A, a proposition and E proposition are contradictories. B, a proposition and O proposition are contradictories. C, E proposition and O proposition are contradictories. D, I proposition and O proposition are contraries. E, I proposition and O proposition are subcontraries. Explanations. A proposition and E proposition are contradictories. This is incorrect. A and E are contraries, not contradictories. They cannot both be true, but they can both be false. B, A proposition and O proposition are contradictories. This is correct. A and O are contradictories, meaning if one is true, the other must be false, and vice versa. C, E proposition and O proposition are contradictories. This is incorrect. E and O are not contradictories. They have a subaltern relationship. If E is true, O must be true, but if O is false, E must be false. D, I proposition and O proposition are contraries. This is incorrect. I and O are not contraries. They are subcontraries. They cannot both be false, but they can both be true. E, I proposition and O proposition are subcontraries. This is correct. I and O are subcontraries, meaning they cannot both be false, but they can both be true. Correct answer. The correct answer is... This option correctly identifies the statements that are accurate according to the classical square of opposition. Immediate inference. An immediate inference is a type of reasoning where a conclusion is derived from a single statement or proposition. For example, from the statement, all toads are green, we can immediately infer, no toads are non-green. This specific type of inference is known as obversion. Immediate inferences use logical operations to create statements that are logically equivalent to the original statement. However, There are also invalid immediate inferences, known as syllogistic fallacies. Questions asked in immediate inference. In questions about immediate inference, you might be asked to determine what happens to a related proposition if the original proposition is true or false. These questions test your understanding of logical relationships and transformations. Solving logical propositions with a table. Let's learn how to use a table to solve logical proposition questions. This will help us understand what happens to one proposition when we know the truth of another. Here's an easy way to do it. The table. We'll use a table with different propositions labeled as A, E, I, and O, and their corresponding truth values. Here's how you read it. A, all S are P. E, no S are P. I, some S are P. O, some S are not P. The table might look something like this. How to use the table. Let's say we want to know what happens to E if A is true. Here's the step-by-step process. 1. Find the proposition in the table. Start by looking for the A column in the table. 2. Identify the truth value. Check the truth value under A. We see a capital T, which means A is true. 3. Check the corresponding proposition. Now look at the E column in the same row. 4. Read the value. You'll see an F under E when A is true, so if A is true, E is false. Another example. Let's try another one. If E is true, what happens to I? Using this table, you can easily find out how the truth or falsity of one proposition affects another. Just follow these steps. 1. Find the proposition column. 2. Identify the truth value. 3. Check the corresponding column for the other proposition. 4. Read the value to determine the result. This method helps you quickly solve logical problems and understand the relationships between different propositions. Question 1. Let's match the list 1 with the list 2. Look at the first proposition in the list where it says if A is false. When we look at the table, we search for the A proposition column and then look for capital F. We then observe that E and I are undetermined. So the correct match is, if A is false, then E and I are undetermined. Now look at the next proposition, if E is false. When we look at the table, we search for the E proposition column and then look for capital F. We then observe that A and O are undetermined. Look at the next proposition, if I is false. When we look at the table, we search for the I proposition column and then look for capital F. We then observe that A is false, E is true. Look at the next proposition, if O is false. When we look at the table, we search for the O proposition column and then look for capital F. We then observe that E is false, I is true. That wraps up our class on the classical square of opposition and immediate inference. Great job, everyone, on tackling these tricky concepts and working through the UGC NET questions. Remember, the key to mastering logic is practice, so keep at it. Don't forget to check out the link in the description for more practice questions and resources. Thanks for joining in today's class, and I'll see you next time.